I'm now going to summarize a project that has been going on off for 4.5 years, and I'm going to do it in 30 minutes. That is, of course, completely impossible, so you're free to harass me with questions and the things that I won't be able to cope with here. I call it nerd level presentation. That means that I will try to explain some of the techniques used in this project, and also, of course, motivation and things like that. Okay, we're talking about tokens like smart cards. And if you're going to do something with smart cards, and particularly if you're going to do enrollment, that means putting keys on smart cards, you have to be true experts in and know a lot of standards. We have people here in this room that are experts on smart card middleware. I think Martin is one of the biggest experts here in smart card middleware. Anyway, this is fairly complex. The state of standardization is not the best in the world. For instance, if you buy a smart card and then you would like to connect yourself to a SIA and get it enrolled, you run into differences because the browser vendors haven't decided exactly what protocol to use. You also have middleware issues. You have initialization issues, like how are you going to set the PIN code? That's typically not something is powered by these protocols. That's where I started some 4.5 years ago, doing a new protocol. After a while, I saw that a protocol wouldn't really solve the problem, so the project has grown quite a bit. Even if you have a nice protocol, you still have so many differences at the middleware or hardware level, so that the protocol would have to be very large and to accommodate all those differences. So I took a more radical approach to this. Why not define a hardware level as well, which is sort of matching the protocol one-to-one? That's, of course, a little bit stupid, you could say, because that means it would be incompatible, for instance, with existing smart cards. It's incompatible with phones, that's true, but phones is really something new. I consider the phones that are out there today as sort of a version 1.5 when it comes to hardware security. So there is still room to actually establish new things. I also thought that the problem with all kind of standards or efforts in that is to reach a critical mass. That means it must be applicable for many things, and we all know that PKI is sort of, that's a powerhouse for two-factor authentication. But there are also some people who use one-time passwords, so I felt that if you do something, it should be able to cover that as well. Microsoft some years ago tried to launch something called information cards, which is sort of an open ID on steroids, and I still think it's a good thing. They have shelved it because they didn't make any money on information cards. This is not really about making money, it's creating something useful, which is not exactly the same thing. Now, the thing with hardware cryptography, like smart cards, is that you know that the key is protected in some way, and none of the protocols out there that are in browsers can preserve that. That means that an issuer cannot see the difference between a software-generated key or a hardware-generated key. And that sort of destroys the whole idea with smart cards. Yes, the user knows that the key probably is in a smart card, but the issuer doesn't know that. And the issuer typically your bank, your employer, your government, or something like that, and they are those who care most about the security, and they set the policy. So what I sort of revised the project somewhere in the middle and introduced what I call end-to-end security. End-to-end security means that it's the issuer that talks to the container. Then there can be things in between, but that should not change the thing. It's really a connection, some kind of virtual channel between the container that contains a key and an issue. For that, you could, for instance, start manipulating PCS11, add extensions to that. I feel that, okay, there are so many cryptographic APIs there. If I would do changes in all those, I wouldn't get anywhere. It would take forever and no one would agree on anything. So I created a parallel IPA that is only intended for provisioning and kept the, let's say, user side as it is. I don't think I have anything innovative to offer on the user side, because when you authenticate, what do you do? Well, you do something like an RSA signature. Maybe you give a PIN code. It's very hard to do something else. That's essentially what you need. But provisioning is, well, I would say, virgin territory, a little bit at least. Now, in order to do this end-to-end security, you need a container and that has some special characteristics. If you're going to do this remotely, you're not going to produce smart cards in a special facility. You're going to provision keys remotely, maybe to phones, maybe to smart cards, directly by end users. You must have some way of authenticating the container itself. Otherwise, you can't say really that I provisioned a key in this container. For that, you need a device certificate and a suitable key that can attest that, for instance, this container is made by a famous smart card manufacturer. It has this serial number. Then the issuer can be sort of discriminative if it wants and say we only accept containers of that brand, or it can accept anything. Anything is possible in between there. Now I'm going to go a little bit deeper down into how this is designed. If you're going to do end-to-end security, and you're going to do it multi-step, because if you're going to issue a PKI, it's not just one step. Because you create a key, you set a key pair, you send the public key to a SIA, you get a certificate back. There are other things as well that can be a part of the process. That means it's a multi-step process. If you're going to do a multi-step process efficiently, you should use a session key. And this, I will just describe a little bit how this session key system works. A session key is a symmetric key, and then the symmetric key can be used to do MAC authentication and encrypt data that is sent back and forth between the container and the issuer. And in this system, you would like the session key to have high entropy, because that's important for cryptography. And you would like both parties, there are two parties involved in this, to contribute to this entropy as much as possible. Therefore, we have ephemeral keys, that means random keys, in both the server end or the issuer end and the client end, using elliptic curve Diffie-Hellman. That's a way to create a shared key. However, that's an unauthenticated key. You don't know anything about who has done that key, but you know that it has it's random, and nobody can steal that on the way if the keys are properly identified. But here we have this device certificate and the attestation key of the container. In one atomic operation, the container reads the public key for the Diffie-Hellman, creates a key pair, signs the public key that is received, and its own generated public key, and as well as session ID. A session ID is needed to have some kind of handle to the session going on. By doing that, a man in the middle cannot actually change anything, as long as you know your own public key. The issuer knows the public key, and it also, of course, must trust the attestation signature from the container, otherwise the scheme doesn't work. Exactly how you create this trust, that we can go on at some other time. I don't want to go into that here. Okay, the protocol I'm talking about called TN2, it uses XML. It's not horribly interesting, but when the server sends down a public key, it's an ephemeral public key. It's just a standard XML representation of a public key. And then the thing sent back from the container is the container's own public key that it has created, the device certificate, and here it is important, this is the attestation signature, so which together with the device signature is sort of the proof the issue needs to have that it's talking to the container. An interesting thing is the trust model. A traditional smart card, the issuer authenticates to the container. That's not a part of the scheme I'm working with, because that's not an internet model. In an internet model, when you have a phone, for instance, you should be able to connect to any issuer, and who is then introducing the trust? Well, it's you that decide what issuers you want to go to. You want to go to your employer, your bank, or whatever. So that part is you, the trust. And the issuer trusts, hopefully, the container, and I guess you as well, since you're going to get a key. Then the interesting thing is, what does the container trust? The initial phase, creating the provisioning session, the session key, it has relieved that, left the issue to the user to decide. But then everything that comes after that is bound to this session key is checked, so that it won't do anything if it doesn't match the session key that was agreed. That is the trust model. That means it only trusts itself, you could say. Now we have a sort of typical scenario here. We want to provision a couple of keys. We want to assign a PIN policy to them. We also have a puck value. If you now have a rather simple container, that's very important. If this is going to work, the container shouldn't be able to need to read XML, for instance. Very few cryptographic containers do that, and it shouldn't have to do networking. It should be, as existing cryptographic containers, pretty primitive. And here we have something that basically requires 4 different objects. If you do that on a network, you would typically create an object, send a signal, create an object, and then you would get a handle back. And if you're going to link that to another object, here we have a PIN policy object that obviously is connected to this POC policy object. Then you will have to give that handle as an input, send a crate, and then get a new handle back. And you would have to do the same for these key objects. That means you have one network round trip for each object. That's very inefficient. I hope I'm not talking much too fast here, just checking time here. Now, this is probably the most complex part of this system, but it's also, in my opinion, the most interesting, how this actually works with these objects. We have a proxy, that's a requirement. A proxy does what I call the heavy lifting. That means it does networking. A cryptographic container doesn't do networking normally. It just has a simple API that you can call. It also does XML processing. I could, of course, have selected a binary protocol, but I felt that it was not so nice. And then the interesting thing is content aggregation and object linking. That means that you can do more efficient things. So the thing I showed on this page actually translates into 4 specific API calls, which first is a create a PUC, and create a PIN, and then create 2 keys. And they can be aggregated, I mean collected as one unit, and then the return is just one object. That means one network round trip, and still it is one end-to-end security. How is this working? I will now try to, the most complicated thing, explain how the XML actually is converted into a very low-level API, and that it still is a one end-to-end security protocol. This is XML needed to create this structure with a puck that owns a pin object, which in turn owns two keys. So this is a sequence for creating this structure in the token. For that, the session key is involved. Each XML fragment here represents a specific low-level operation. This one is called create key entry. And in order to make sure that we're still on track, the session key is merged with the name of the actual API, a sequence counter. The sequence counter is something which is incremented for each low-level call. And the point with that is that if, for instance, this proxy is doing something wrong, maybe it's completely corrupted, so it forgets one of the fragments or tries to insert something or change order, this MAC will not match because that is read by the container. So here you have the session key, the API name, sequence counter, and then all the parameters that the issuer have asked for are mapped. And this is checked when the container is called. The interesting thing here is how the linking is working. If you remember the picture, there was an arrow from the key to the pin policy object, but you don't see any arrows here because this system is, the XML level is using object embedding. That means here you have a pin policy object. It embeds two key objects. That's an indirect way saying that they are owned by this object, which in turn is embedded by a PUC policy object. How is this linking performed? Well, here we have the name, which is mapped. And now we're going to how it actually works. When you create an object locally, you use low-level handles, but you never send them on the wire because that would be stupid. When you create a pin, you get a handle. And that handle is used as input to, in this case, the create key entry. And then the create key entry API checks that this handle actually points to a pin policy object, otherwise it's sort of a syntax error, and it takes the ID that is associated with this already created object and does the MAC operation. So if anything is wrong here, this is wrong type, the MAC doesn't matches, it will just abort the entire session and go back to square one. That is how end-to-end security is working. And this is, I call it then object aggregation and object linking. So here you can see some extracts of this provisioning API. Okay. After, okay, let's go back to one. When you have created the keys, you have the public keys, which you want to have certificates for, and you send them to the CA. And you add an attestation. The things that comes from the container is called attests. So you have an attestation that uses a derived version of the session key. It's used all the time, and the session counter as well. And it it then does a MAC operation with the name of the key and the public key. Here we have the name, and here we have the actual public key value. So that the issuer can verify that it got, first must verify that it got the number of public key it requested, that they have the name, and then it verifies that the attestation, which is a MAC, actually is correct. So this, now we have done two steps. First it was the issuer that asked for keys to be created, and now as a response we get two attested public keys. That means that sort of rather traditional stuff like proof of possession, it doesn't really, is not needed here. Assuming that the trust, the container, and the whole ID with session keys and attestation is better, because it says, well, I made these keys. That's what it says. So you don't have to do a private key operation again. That wouldn't add anything. As long as you trust the container, of course. So, and then the last step is that you get the actual certificates. And the certificates, in sort of traditional ways, you just fit the certificates to the matching public keys. That would break the end-to-end security scheme. It's very important that everything is kept in one session, because if there is something wrong here, the idea is to do a full rollback. So only if you succeed with all operations, you should have done something in the container. Otherwise, it should go back to its original state. And that is, for instance, the situation what you have when you get a new credit card. You're supposed to cut the old one and put the new one in the wallet. Here you do it virtually, and either you succeed with that operation and get a new credit card, or you still have your old credit card left, which may be important, so you're not dead. This also is, yes. So the MAC here is then done over the certificate and over the key and the public key that is supposed to match, so that the certificate's not accepted without doing a MAC test. Then you can see that there is it says a finalization request. We are not done, and you must have some way of saying, no, I'm ready, I have provisioned all the keys I wanted. So the last thing you do is close, and then you take the handle. You always use a low-level handle that's done by the middleware, and it's MAC'd as well. That means that the last, now I'm ready, it also has a MAC, and if it's successful, it generates a receipt, which is sent to the issuer, so that the issuer actually gets a receipt. Well, the provision is succeeded. If there is something failed, the issuer won't get anything. That is sort of a quality control. It's rather interesting here. If you have sort of only 9 out of 10 of requests actually generates a receipt, you probably have a quality problem somewhere. It can be anything. It can be a software problem, or users don't understand the process, or whatever.
What if the receipt gets lost?
If the receipt gets lost, that's a situation where the issuer don't know if the process has worked, and of course there are no fantastic thing you can do. I would say that an issuer should consider all credentials as invalid until it has received a successful receipt. That is a strategy, but it's a very valid question, absolutely. Okay, since I said that some people like one-time password, you must have that as well. And here's an example. This also uses object embedding. That means that you hang things on the certificate. In fact, the certificate or the key entry holds all stuff, even symmetric keys. That sounds probably very strange, that a symmetric key would have a certificate. That has to do with that I didn't want to do a specific API for symmetric keys. That would be very stupid when I had everything else running, and there are also key management operations. That means that we have one way of giving keys a name, and that's a digital certificate. That works for anything. It even works for symmetric keys. And then you get a very high symmetry, and that's important because you want the container, you want the protocol, everything to be as simple as technically possible. I haven't tried to sort of to do a specialized. Now you will create, let's say, a key pair, symmetric key pair, asymmetric key pair, but the private key will never be used. So what? It doesn't matter. Anyway, we have symmetric keys. You have properties, a lot of things like one-time password, but also weekend connections need properties. So you can have arbitrary properties associated with keys. Must just check the time or not. Okay, good. And to make things a little bit more user-friendly, there are logotypes as well. That is a hope that there will be better TLS GUIs, where you will see things like a credit card or something like that, rather than the ugly CN equals blah blah blah. That doesn't say too much to people except us, of course. We know everything about certificate attributes and love to read them, but not everyone else does. Yes. Yeah, okay. This seminar was called Open Security Hardware, and you haven't seen much of that. The hardware doesn't exist yet. What does exist is an emulator, a specification, unit tests, a lot of things. The next step is converting this into open security hardware. There will be a guy actually presenting a token which is very similar to what would be needed. I think it was 1500 today, the GNU token, and that's well very close to what I am trying to accomplish. I think that the GNU token could actually implement the SQS API. That would be possible. It's a little bit, maybe you need a little bit more memory. Because the idea is creating a reference implementation that the real vendors of smart cards can use as much as they want. One of the outcomes, of course, which I sort of started with, this one, is the SQS API would require a single driver because it's so fixed. It's not very flexible. It does this and nothing more. So the idea was that instead of you having qualifying different software for different hardware, the hardware vendors would rather qualify against a software package that implements the SQS API. It is sort of turning the things upside down. If that will work or not, that depends, of course, how successful this will be. And that's why I try to make it as generic as possible. Security hardware in devices is coming in a big way, and the standards are not yet established, so there is room for doing something. And I don't see a point of having lots of new enrollment protocols and that are proprietary. It will be very expensive. That is essentially my presentation. I have probably forgot a lot of things here. Yes, I can take one thing. And one of the early reviewers wondered why I didn't use TLS, because this scheme with session key is very much like TLS, which is based on that you first create a session key and then you do everything in using that key. Or there are two keys actually, and you use rolling max as well. But why didn't I use TLS, which is sort of established? And that is because let's say that you wanted the issue to say, well, create me a key and let the user set a PIN according to this policy. How is the user going to interact if you have a TLS tunnel between the container and the issue? There is no way you can break into that. Then you must add a side channel, and that sounds like a horrible idea to add in another channel for doing UI operations. And that's just one of the many things. Then we have this XML stuff that you want to have a fairly fat program that does the XML processing and keep the container. It should only understand simple binary APIs. And that doesn't work if you have a complete end-to-end security without a proxy, because then the container would need to read XML and understand complex structure like this embedded pin and puck objects. That would be a very complex container, and it would be no better than this one. I would say the opposite. Okay, I think I'm done. And if you're interested, well, you can talk to me. I will be here 2 days.
Do you have the fat client already?
Yes, the fat client is the easy one. It's, I don't have the thin container in hardware. The fat client, yes.
Do you know of any other efforts to make this key attestation?
Yes, I've borrowed a bit from the TPM work from PCB, and it's also similar to Global Platform as well. They have something, but Global Platform have not gone the whole way and created the protocols and webs, and they are talking about it, but they haven't done it, and they have had ample of time. And so there aren't too many actually, but there will be competition. I'm sure about that. I just don't know it. It's your turn, I guess, or was it no?
Det känns som en pausa.